This video is going to go through the first steps in the derivation of the eigenfunctions for the hydrogen orbital energy problem. So what we have so far is the here in this first term is the solution, or is the differential equation, the kinetic energy part of the Schrodinger equation, and in the second term here is the Coulombic potential function. And so to solve this equation, we're going to go through a few steps. And what we're going to do is we're going to see that we can eliminate the angular components because the potential energy is only dependent on the distance, which makes sense for Coulombic potential. So we're going to eliminate the angular components. And in doing so, we're going to see that our solutions to the rigid rotor come up as well. So we can already see right now a great resemblance in these two terms here of our equation and the solutions to the rigid rotor. So to do this, we are going to first recognize that the potential does not depend on anything other than the distance. And what that's going to mean for us is that our wave function, which is a function of r and theta and phi, can actually be split up into three different functions. So a function that just depends on r, a function that just depends on theta, and a function that just depends on phi. And it's reasonable for us to do this because the potential is independent of the angles there. And I'm going to abbreviate them in this video as just r, theta, and phi to avoid writing out all of the various variables. So now I'm going to take this information that our wave function is actually three different functions, each dependent on only one of the variables. And I'm going to take that and I'm going to do I'm going to put that into the equation and do a little bit of rearranging that might look strange, but will make sense after I have done it. So what I'm going to do is just write out here negative h bar squared over 2 times the mass of the electron. And then I'm going to multiply this by our function of theta and phi over r squared. And I'm doing this because when I take the derivative of our function with just respect to r, the two functions of theta and phi are treated as constants and are pulled right out of the derivative. And so this is equal, so now we take this and multiply by the derivative with respect to r of our r squared times the derivative with respect to r of our function r. And to this, I'm going to write this again in a way that looks a little weird. So I'm going to write 1 over 2me times our radial function r over r squared. And then I'm going to put this in brackets. And here we're going to put this negative h bar squared is on the inside. And that's going to be multiplied by the remainder of the first term, so up there. So 1 over sine theta times the derivative with respect to theta of sine theta times the derivative with respect to theta of our functions theta and phi. Now, I could, of course, properly take out that phi, and I'll show you why I'm not doing that in a second. And to this, we are going to add the final term, 1 over sine squared theta times 2 derivatives with respect to phi of our functions of theta and phi. All right. And now for this, for the rest of this, I of course have the remaining term and also what it equals. So that we have to subtract our e squared over 4 pi epsilon naught r times our function of r, theta, and phi. And this is equal to the energy times our functions of r, theta, and phi. Okay, so why have I written it out in this weird way? Well, I want to show you why I've done that. And to do that, we're going to imagine that we divide this by 2i. Now, once I put this 2i here, hopefully you can recognize this whole term in the brackets as the Schrodinger equation for the rigid rotor. So this is the Hamiltonian for the rigid rotor operating on our functions of theta and phi. So here our functions of theta and phi are our spherical harmonic functions. And when we operated on our spherical harmonic functions with this term here in the brackets, this operator, we ended up getting the energy values for the rigid rotor multiplied by our harmonic oscillator, or our spherical harmonic function, sorry. So we don't have this 2i here. I put that back in. But what we have without the 2i is actually the L squared operator. So remember that the total energy operator, so this Hamiltonian for the rigid rotor, is equal to the L squared operator divided by 2i. So since we don't have that 2i, this whole term in the middle is just our rigid rotor operator, or our angular momentum operator for the rigid rotor. And so when we operate on our spherical harmonic functions, with the L squared operator, we return the angular momentum, which is h bar squared times L plus 1 times our function of theta and phi, our spherical harmonic functions. So now we can come back here and substitute this in for the second term, and that's going to greatly simplify our problem. So we come back here and we say minus h bar squared over 2 times the mass of the electron times our function of theta and phi over r squared times the derivative with respect to r of r squared times the derivative with respect to r of our radial function r. And then this is plus 1 over 2me times r over r squared. And then we're going to replace this whole term in the brackets with L squared operating on theta and phi. And when we operate on theta and phi with L squared, what do we get? Well, we always get h bar squared L plus 1. So I'm going to go ahead and erase this and write in h bar squared L plus 1 times our functions of theta and phi. And now we do the remaining part, so we subtract e squared over 4 pi epsilon naught r times our function of r and theta and phi. That's equal to the total energy times our functions of r, theta, and phi. Now you can see that theta and phi are in every single term. So what we're going to do is simply eliminate them from the equation, take them out of every term, and that shows that our total energy is in fact not dependent on theta and phi. It's not dependent on the angle, and that makes sense for our Coulombic potential. So I'm going to rewrite this, and I'm going to pool these two terms that are each dependent on r, and I'm going to rewrite this as negative h bar squared over 2me r squared times the derivative, and now that we've removed our angles, we just have a regular derivative, not a partial derivative. So the derivative with respect to r of r squared times the derivative with respect to r of our function r. And then we're going to add to this h bar squared times L plus 1 over 2me r squared minus e squared over 4 pi epsilon naught r times our radial function is equal to the total energy times our radial function. So here we have lost the angle components for the total energy. You can see the energy only depends on the distance, the radius r. So this is a solution or a differential equation we can solve. I will provide the solutions here for you if you're interested, but normally we're just going to look these up in the book. So these solutions are of course normalized. They're polynomial solutions with respect to r, and then they have this exponential decay function as well, because they need to go to 0 at infinity. And these functions are going to give rise to the orbital shapes that we know and love. And remember that our orbitals, our total solutions here, are functions of r, theta, and phi. So the total answers are going to be these radial functions, which are dependent on the quantum numbers n and l, multiplied by the spherical harmonics that we took out that are dependent on the quantum numbers L and m sub L. So if we want a complete picture of the orbitals, we need to consider both the radial functions that are solutions to this equation here and the spherical harmonic functions that are solutions to the rigid rotor problem. But the solutions here, these r and l's, they're going to be equal to, first, this term here. This is going to be a normalization term. So it's n minus 1 minus l factorial over 2n n plus l factorial. And then this is multiplied by 2 over n a naught raised to the l plus 3 halves power. This is multiplied by r to the l, and then times e to the minus r over n a naught. And then this is all multiplied by another polynomial that we're going to write here. So this polynomial is l to the n minus l minus 1 and 2l plus 1. And this is a function of 2r over n a naught. So this l and these two indices here is just another type of polynomial. So I'm going to write that down here. So this polynomial is, we can write it here as l to the nk of x is equal to the sum from m goes to 0 to n of minus 1 raised to the m and then over n plus k factorial times n minus m factorial times k plus m factorial times m factorial, and then this is raised to x to the m. So to get this, we would take 2r over n a naught and plug that in for x here. Then the n and k are various indices based on L and m, which give us a different polynomial. And this gives rise to the nodes that we know to expect in the orbitals. And the shapes come from the spherical harmonic functions. So with this, hopefully you can see a little bit better how we eliminated the angular components and where these radial solutions come from for the hydrogen atom and its electron.